In this lesson, we're going to be looking at the distinct or coincident lines that you can get when you have a system of linear equations. Now, if your vocabulary is good, you probably already have an idea of what that might mean, but I'm going to show you what that means. Actually, I've already shown you this before. In the first lesson, where I talked about solving systems by graphing, some of the systems we had, I'm not sure, I think these are the exact systems, and so you can go back and take a look at that lesson if you like, but I'm going to refresh your memory. So we had some systems with some unusual results. Here's the first one, and if you take a look at the actual equations of this system, the two equations, you might notice that they both have the same slope, but the second one doesn't have a y-intercept. But of course it does have a y-intercept, it's just the y-intercept is 0, and so we don't bother writing plus 0, it's just understood to be there. So that being the case, we end up with these two lines. This is the line y equals 2x, and the blue line is y equals 2x plus 4. They have the same slope, and because they have the same slope, that means that the two lines are actually going to be parallel to each other. And because they're parallel, that means they're never going to touch each other. They will carry on infinitely far in each direction, and they'll never cross. So how many solutions does this have? When we talk about a solution to a system of equations, we're looking for the point where those lines cross. But the very definition of parallel says they will never cross. So we end up with no solution to this system. That's easy enough to see algebraically, and it's easy enough to discuss just in terms of the idea of lines being parallel. What would happen if we tried to approach this algebraically? In another couple of previous lessons, we've looked at a couple of techniques that you can use to solve algebraically. There's substitution or elimination. And either of those will work here. So let's start with substitution. So I'm going to call this equation 1. I'll call this equation 2. And you can see both of them are in the form y equals mx plus b, and in particular both of them are isolated for y. So what I'm going to do is I'm going to substitute equation 2 into equation 1. So equation 1 started as y equals 2x plus 4, but wherever I had a y in equation 2, wherever I have a y in equation 1, I'm going to replace it with the y value from equation 2, which is 2x. So instead of this y, I'm going to put a 2x there instead. And if you're thinking ahead, you probably already realize this looks pretty odd. 2x equals 2x plus 4. I've already got my 4 on the right side, so why don't I go ahead and try to move all of my variables over to the left side, subtracting 2x from both sides, and I end up with this very unusual result, which is 2x minus 2x is equal to 0. 2x minus 2x is equal to 0, and I'm going to go ahead and write it in this time. Normally I wouldn't write these zeros, but it's important. And something that's very important here is you do have to write the 0 on the left side. There always has to be something on either side of the equal sign. So this 0 has to stay there, and 0 plus 4 is simply equal to 4. And look what we've done here. By trying to solve this system, we have produced a mathematical statement that is obviously false. And if we have a false statement, then that means that this can't possibly be true. That means that there is no solution. So therefore we have no solution to our system. And just to show you that you could have gotten the same thing had you done elimination, very quickly, y equals 2x plus 4. Y equals 2x. That's equation 1. They're the same equations, 1 and 2. Now I'm going to say equation 1 minus equation 2. y minus y is equal to 0. We have to write the 0 because the equal sign has to have something on both sides. 2x minus 2x is equal to 0, plus 4. 0 equals 4. This is impossible. Therefore, no solution. So whether we say it's a false statement, it's an impossible statement, they all mean the same thing. And no solution is consistent with what we already knew was going to happen based on this diagram. Okay, second example. Y equals 2x plus 4 and y equals negative x plus 4. The graphs are shown. 2x plus 4, slope of 2, an intercept of positive 4, slope of negative 1, and an intercept of positive 4. So this one has a solution. And in this case, it has a solution at this point of intersection that has an x value of 0 and a y value of 4. The lines aren't parallel. We get one solution to the system. Now, if you tried to solve this system algebraically, we've done this already. We've done this many times. We're just going to go ahead and get the result that we would expect, the 0.04. So in this case, I'm only going to use one method. And since they are stacked up so nicely, the y's are already set to be the same. They have the same coefficient. So I'm just going to say 1. And because the coefficients of the y have the same sign, they're both equal to positive 1, I use subtraction to eliminate them. 1y minus 1y is equal to 0. Be careful here, I'm doing subtraction. So this is 2x minus negative x, which is the same as 2x plus x, which is equal to 3x. And this is 4 minus 4. 4 minus 4 is equal to 0. Again, I didn't need to write this plus 0 because we still end up with 0 equals 3x. And I want you to try to understand that this is not the contradiction we had in the previous statement. What value of x, when you multiply it by 3, multiplies and gives you 0? And there actually is a value that works for. The answer is 0. 3 times 0 is equal to 0. So I don't want you to immediately think, oh, there's a 0 on one side, I have to throw this away. Sometimes it's a perfectly valid result. Another way, let's isolate it. Divide both sides by 3. So obviously 3 divided by 3 just gives me my x. I'm just going to put it on the other side. And 0 divided by 3 is asking the question, how many times does 3 fit into 0? And the answer to that is it fits in 0 times. So now I have my value for my x, and then I'm going to sub x equals 0 into either equation. So I'm just going to put it into equation number 1, and I end up with y equals 2 multiplied by 0 plus 4. 2 times 0 is 0, plus 4 is simply equal to 4. Therefore, my solution is the point x equals 0, y equals 4, or 0, 4, and that is exactly what we predicted from our graph. So nothing new about that one. And finally, here we have two equations that look different, but when you actually graph them out, it turns out that they are the exact same line. So that means that these lines are coincident. They lie on top of each other. There are infinitely many solutions to this system. Everywhere that they touch is a solution. So what is going to be the result when we try to solve this algebraically? All right, taking a look at what I have here, I have two equations, equation 1 and equation 2. And equation 1 is already rearranged for y equals x minus 3. So this one is already set up to do substitution. And the x's and the y's don't have the same coefficient, so I'd have to do some sort of multiplication. So I think I'm going to do substitution. I'm going to sub equation 1 into equation 2. And so I end up with equation 2 is 4x minus 4, but instead of the y value, wherever I see a y value in equation 2, I'm going to replace it with this y value, but that's this expression, x minus 3. So I put x minus 3 here, and that is equal to 12. Now expand this out. 4x minus 4x, negative 4 times x is negative 4x. Negative 4 times negative 3 is plus 12, and that's equal to 12. 4x minus 4x is equal to 0. I'm not going to skip any steps here. 0 plus 12 equals 12. But what is 0 plus 12? That's just equal to 12. So 12 is equal to 12. Is that any surprise that 12 is equal to 12? No, this is a true statement. As a matter of fact, this statement is always true. It is always true that 12 is equal to 12. Right? Same thing would have been true if I had gotten any number equal to any number that's the same. So always true means we have an infinite number of solutions. No matter where you go on these lines, you have a solution. That's essentially what this is saying. So we have an infinite number of solutions. Okay, so now that we've done that, just a bit of a summary here. One solution, that's the typical case. That's what we're normally going to find. You find the value of one of the variables, x or y, and then you solve for the other, and you end up with some sort of point xy. With no solution, you end up with an untrue or a false statement. So for example, 0 times x equals 2. There's no value of x that you can multiply by 0 to end up with 2, so it's never true. When that happens, you have distinct lines. So that means you have two lines that are parallel to each other. They're never going to touch. And for infinitely many solutions, you end up with a statement which is always true for any value of x. Or another way of thinking of this is it just doesn't have any x's or y's in it. So 0x equals 0 because 0 times x is always 0, so 0 equals 0. That's always true. And these are coincident lines. These are two lines that lie on top of each other. One last example. Write a linear system with infinitely many solutions or no solutions. So can you take your understanding of what we just kind of summarized on the previous page, infinitely many solutions or no solution? So no solution means two parallel lines that are distinct from each other. Infinitely many solutions means we have two lines that are the same. So for infinitely many solutions, we have the same line. So let's go ahead and just pick any line that we want to. Y equals 3x minus 7. And I need to rewrite this equation in another form. So one thing I could do is take equation 1, and I'm going to multiply equation 1 by 2. And I end up with 2y equals 6x minus 14. So that's equation 2. I'm done. That's all I needed to do. If I want to make things a little bit more confusing, if I'm trying to trick someone, then maybe I'll also rearrange this and make it look a little bit different. So maybe I will bring the negative 14 over to the left side, turn it into positive 14. I'll leave the 6x where it is, and I'll take the 2y, positive 2y, and bring it over to the other side and make it negative 2y. So I might make another equation and say there's my, so 1 and 3 are distinct. And yet they don't look the same. So this equation and this equation, when you first looked at them, you wouldn't look at those and automatically say those are the same line. So take a little bit of work. No solution. For no solution, that means we have, I realize I've done these backwards. This one is not, oh yeah, no, infinitely many solutions. I haven't done them backwards. This is correct. Infinitely many solutions means it's the same line. This is where I went wrong. These lines are not distinct. These lines are coincident. I apologize for that. I'm not going to redo the tutorial just for that. These lines are coincident. For no solution, I want distinct lines. I want lines that are parallel. So let's draw two lines that are parallel. Y equals negative 5x plus 3. And in order for me to have a no solution means that the slopes have to be the same. So the slope has to be the same, and the y-intercept has to be different. And that's easy enough to do. We can just read that right off of here. So let's write another line that has the same slope, negative 5x, and has a different y-intercept. So let's say negative 5x minus 2 this time. Same slope, different. Now I could just stop here, or I could manipulate this a little bit to make it a little trickier. So in this case, let's go ahead and I think I'm going to take equation 1, equation 2. I'm going to take equation 2, and this time I'm going to multiply it by negative 3. So I end up with negative 3y. Negative 3 multiplied by negative 5 becomes positive 15x. Negative 3 times negative 2 becomes positive 6. So even though you're doing this work and making things a little bit harder to see, you still have to show where this is coming from. So I would always want to see this first step, and then if you want to make it a little trickier, you go ahead and do that. And again, let's not leave it quite so obvious. So in this case, I think I'll bring the 15x over, so it becomes negative 15x minus 3y. Actually, let's move the y to the other side. So that becomes equal to positive 3y plus 6. So there are my these are two distinct lines. They are parallel to each other and they have no solution. I'm not going to go through this last step of solving the system. I've shown you some examples of what's going to happen when we do that. You could do that on your own to try to solve these two systems. What if you were just given these two systems blindly? Could you come up with the conclusion that this one has infinitely many solutions and that this one has no solution? And that's the end of our tutorial.